Alright, so I decided to post a follow-up video to the update that I gave a couple days ago about using the Python API to play with the RPiSoC. I thought that I'd introduce you guys to PSoC Creator, because it's really where you're going to find the strongest feature set of the RPiSoC using its native design environment, because by design the Python API really can only expose a subset of the functionality of the RPiSoC. So while it's really awesome for an offloading tool, there's like tons of stuff you can do with it to offload certain services and give it some extra hardware to use. It's really only so much you can do. You can only be so flexible with it. But PSoC Creator really gives you that flexibility that you need. And I find that most people, while they might be scared off from the visual aspect and the C programming, will find that it's actually not so bad. The visual interface makes it really easy to kind of see your full design just at face value and before you even get into programming it. And then the C programming itself is very abstracted from typical embedded systems applications. So like, while it is C, it feels very much like C++, and you'll see why I say that in a minute. So let's just get started with the schematic. That's where I like to always start my programs, is in the schematic, because like I just said, it kind of gives you an idea of how everything's going to unfold. So the first thing we're going to do, and everyone's going to have to do, is drop in your bootloadable component. Easy as that, really. I had it copied from another project. You can also search for it in the component catalog and then change the dependencies. Got a right application version and then dependencies right here. But it's preserved if you just copy it from another project. Easy enough. And then with that in mind, you make sure that your build settings are correctly identified as bootloadable, because that's what this is. This is a bootloadable program. Alright, so that's, now we have it's set up and ready to go. What we're going to be doing is essentially playing with some servo motors. Easy enough, really. You could obviously do this through Python too. This isn't really a complex application, but it's kind of nice to see how it's done from scratch. I got a joystick from Adafruit the other day because I made an order and I saw it in their product page and I was like, I'll grab a joystick. I'm sure I could think of something to do with it. And this is what I'm going to do with it. It's good an application as any. I'm going to move around the pan tilt bracket for our face tracker using the joystick, which is kind of cool application. It's kind of fun. It should be pretty easy to build, so I'll show it to you guys here. So to get started with that, the first thing we're going to do is drop in our ADC, because we are going to need to get some analog readings off of the joystick. So that has the X and Y axis. We need two different analog readings. So the first thing we're going to do is we're going to configure this ADC to the way we want it. Only need to be in single-ended mode for the input mode. We only need one configuration for it, but if you wanted multiple configurations, you could, and then you could tell in your program which configuration to load up to the ADC. But we only need this one. We're going to be using a multiplexer, so we're going to want to do multi-sample, but I'll explain that in a second. Keep 16 bits resolution. If you need more SPS, go lower. If you don't care about SPS, go higher. Keep it 16. I feel like it's the sweet spot for most of the time. The multi-sample reduces the SPS, but at single sample, this is good enough for audio. Play with some of these other configurations. This means that it'll only go up to 1.024 volts, but I don't really like that because this thing can read up to 5 if we're using the PSoC's power rails to guide it. So we'll use that as a reference voltage. It's fine. That should be good. Easy enough. So as I just said, we're going to do this with a multiplexer to make this a 2-channel ADC to read both analog values. You could alternatively just use another ADC. Just drop it in. That would be equally fine, and then just one of them takes care of the X axis reading, one of them takes care of the Y axis reading. But I'd like to, for purposes of demonstration, show you another way to do it. We're going to use an analog multiplexer, and there are a lot of them to choose from. So we're going to use this one, but I'd like to kind of look at the other ones at least so you kind of have an understanding. This is a hardware mux, which is really useful for if you are very timing sensitive and you don't want to do it in software, because this one is a software mux, so you'll tell it to do stuff with your API, which simplifies things a little bit. But this one would be implemented in hardware, and you select which channel to choose on this pin right here. So you you would write a 1 or 2 or 3 or 0 to this pin, and it would disconnect the previous channel, connect the new one. It would take 2 clock cycles essentially to do it, and it would be doing it separate from the CPU. So it's really useful to certain applications, but we're not going to do it that way. You could also, even probably more useful for this application would be a sequencer, since we're just switching between 2 channels. The sequencer, it's similar to a mux, except in the sense that you don't tell it specifically a number to go to. You just tell it to go to the next one, so it'll go 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, instead of this one where you can just tell it go to 2, go to 3, go to 1, or whatever you want. So we're going to just be using the mux dog. It's the most common one to use. This is currently configured as a 4-channel, so this is a 4-channel ADC right there right now. You could make this, if you wanted to be crazy, make it a 64-channel, but we don't need 64 analog inputs. That's not really necessary for us right now. You could also make them 32 differential. So you can make this differential and make this 32. Make a differential multiplexer. But we don't need that either. We're just going to make this single, just like so. We're going to make this 2-channel. This is a simple little 2-channel ADC now. And we will connect 2 pins to those multiplexers. So we're going to jump into the pins. We need a digital analog pin is what we want, yes. An analog pin. Copy that. 2 analog pins. We're going to change the name to make them meaningful. It's our x-axis. It's our y-axis. Alright. And with that, our analog readings are totally done. So these pins will be reading in values, analog values from the joystick, from the 2 potentiometers that are inside of it. And depending on what channel is selected on this multiplexer, it'll feed it into the ADC, where it will convert that analog reading to a digital value, and then write it to the servo driver, which we have not yet put in. But let's put in a servo driver. So we're going to make one out of a PWM channel very, very easily. So this is our PWM, which will, in a moment, be a servo driver. And I'm going to call it a servo driver, so I know what it is. I'm also going to change the names of these because I like to have meaningful names, or at least easy to remember names for when I'm programming it. Alright, cool. PWM, let's change some of the configurations. I want it to be a 16-bit. We could change this to max, but it doesn't know the frequency yet because it's not being clocked by anything. I'm going to get rid of the interrupts because we don't really need to do interrupts here. Not really a big deal. Let's give it a clock so it can calculate its frequencies. If you ever used servos before, you know that they are very particular about what frequency is being given to them by the PWMs, but what the temporal period is essentially. They like it to be 20 milliseconds. So let's make sure that we adhere to the data sheets. Let's make this 3 megahertz. Okay. I know that I'd want it to be 3 megahertz just by design here. It doesn't look right. Let's change this to 60,000. Alright, so when this is 60,000, the period is 20 milliseconds. Right, that makes sense. We're going to change both of these compare values too. If you know servo motors, you know that they want to be period values for the pulses to be between 1 and 2 milliseconds, essentially. So for this PWM, that would be between 3,000 and 6,000 compare value counts, because that would be between 5 and 10% of the maximum period. So we'll go right in between that. We'll make the neutral position as our starting value. That's where it's going to start now. So you can kind of visually see what each PWM is creating. You got a 20-second period with the little 1.5 millisecond pulse right here. Alright, nice visual interface, easy to understand. Alright, so now, with that, it appears that your design is actually complete. Everything's in here that you need, except for, never mind, said book too soon, we need to output these PWMs to something. I knew there was something missing. So we just drop some pins onto these. There we go. And now let's rename those so that they're meaningful. Pan. Tilt. Alright, now we're good. And so now that we've got our software kind of envisioned here, we can see it on our schematic, we want to map this virtual program to our physical pins on the RPiSoC. And the way you're going to do that is with your design-wide resources. So it's the, let's see, port 01 is one that I chose for this one, which is fine, let's keep that. Do port 00 for this one, put them right next to each other. So this is where the two PWM data lines will be coming out of. So the tilt you would connect to port 00, pan to port 01. And those are just pretty much arbitrarily chosen. This one, port 46, this is where your analog readings are going to happen. Some pins prefer certain locations, but it's not really necessary. We don't like, for instance, if you had an IDAC, you'd want to put them on one of these if it was high power mode. We don't have an IDAC, so I could use those if I wanted. Just for the sake of simplicity, I'll put it next to the other one, 445. You can, which is really nice. So this means that your software can kind of change your hardware. You don't have to rewire a bunch of stuff if you just change your pin mappings. Saves a lot of time, or at least a lot of trouble. Alright, so with that, our design is done. I went ahead and wrote the C code ahead of time. I'll run through it real quick just so you see it. I was going to just do it in like live, but it turned out that it would make the video really, really long, and it would make me feel very self-conscious about my coding practices. So I just have it pre-made here, and I'll walk through it real quick for just a minute so you can kind of see that it's not so bad. I always just do this in the beginning, always, because I just, whenever I start a program, I think ahead of time what kind of constants I would need, so it's just some preprocessor stuff, not important. And then the first thing you do is you start all your components that you have into your build. So like I was saying before, while it's C, it feels very object oriented. So you have your component here, your component name or your instance name, and then your method essentially, but this is a function associated with that component. So instead of, you know, an object-oriented stuff like in C++ or in Python or whatever, you would say adc.start, and in PSoC Creator you say adc_start. So it's functional programming that tries to be object-oriented, which I think it makes it very comfortable and easy to use. So the C programming is not exactly scary for people that aren't familiar with it. Anyway, so I'm just defining some 32-bit numbers here that I know I'm going to be using in my main loop here. First thing I do is I get analog readings in a kind of convoluted way. I did it purposefully this way because it's really the best practice. You could have alternatively just done ADC, AMAX fast select, and then just done an analog ADC read. It's just been 2 lines to do this whole thing. But I decided to do it this way because it's best practice for if you have a more complex application. You stop your conversions on your ADC so nothing is conflicting. Then you switch your channels of your analog multiplexer, and then you give it a little time. This is more than enough time. In fact, you don't really need it. I just put it in there because it's best practice. And you could also have some kind of hardware dedicated to deciding the exact amount of time to wait, but it's not that important. Then I started the conversions back up, waited for the conversions to be complete. Since we're using a reasonably quick ADC, it pretty much happens immediately. But in case you were using like 20-bit ADC, you might have to wait for the result for a few clock cycles. So just put this here just in case, and then you get the result when it's done reading it. You do the same thing for the other analog value. You just switch the AMUX value there. Could have done that in a for loop too, actually. So thinking about it now. Then I converted the values to voltages because I'm more familiar with that. And then just did some linearization of the angle that you're reading from the joystick and mapped it to another set of data, which would be the comparison value. So it was just two separate states of data, and I was looking for a linear map between the two. Pretty common practice, easy enough. Then I wrote the comparison value, and that should change the position of the servo. And with that, everything's done. Pretty easy enough, really. Nothing too complex here. And you could even simplify this a lot, but for purposes of demonstration, good enough. I will build the project, and I expect that it's fine. It takes a while the first time you build it because it has to generate all the source associated with the program. So all the components that you dropped in, it has to go find all the source associated with it. It takes a minute to do it your first time, but then after that, when it's just compiling your software, it only takes a second. Alright, now it should be good to go. No errors or anything. Seems good. Now all we do to program it is we plug in our RPiSoC using a micro USB cable. We flick the programming switch into program mode. We reset the board, and now it's ready to be programmed. Go into the bootloader host tool. You can tell it's ready to be programmed because the onboard LED will light up, and this little guy will be in your bootloader host tool. See, if I were to flick the switch back and put it into run mode, it'll go away. There you go. Put it back into program mode. Goes back in. Then I just download the program to my RPiSoC. And easy as that, now it is ready to run. And we're going to look at it right now. Hopefully it works. Alright, and now we have the finished product. So let's see if we can turn it on and run it. Alright. So cool. And they could definitely use a little more calibration, but those numbers were pretty arbitrarily chosen, so pretty good for his first try. Easy enough. Fun to play with. Map this on some kind of robot vehicle and control the camera. Take some pictures with the Pi. Be responsive. Alright, there you go.